Hi, and welcome to Physics 2211 Lab 1 Constant Velocity. This will be the table of contents for my lab report. The purpose of this lab is to compare the observed position of an object traveling at constant velocity to the predicted position from a computational model. The object we are analyzing in this lab is a roll of tape. Tracker software was used to observe the position of the roll of tape, whilst the computational model was used to predict the object's position. Beginning with some key principles, Newton's first law states that an object will continue to move at constant velocity when experiencing zero net force. Newton's second law states that the net force equals to a change in momentum over a change in time. Newton's second law can then be used to derive the velocity update formula, where the final velocity vector is given by the initial velocity vector plus the acceleration multiplied by a discrete time step delta t. We also have the position update formula, which will be used extensively in our computational model. The position update formula shows that the final position vector is given by the initial position vector plus the average velocity vector multiplied by time step delta t. For the experimental procedure, a video was first recorded of a roll of tape moving with constant velocity. This video was then imported into Tracker and the tape's position was tracked frame by frame. Next, a computational model of the tape's predicted position was made in GloScript. Finally, the data from both the computational model and the tracker software was then used to create a spreadsheet of data to compare the observed and predicted positions over time. However, we had to make several key assumptions when creating the computational model. It was assumed that there was no air resistance, no friction, and no parallax error when filming. It was also assumed that the roll of tape could be represented by a single point mass, that there was no movement in the y direction, and that the net force on the tape was zero. After comparing the actual predicted positions of the tape using the tracker software and the computational model, we saw that the computational model overestimated the actual position of the tape with increasing error as time went on. For the tracker analysis, this is the experimental setup where the roll of tape was pushed alongside a ruler, starting at a position of 0.9500 meters and moving left towards the origin. Here, the system we are analyzing is the roll of tape and its movement. The surrounding consists of the table, ruler, and the initial push that got the tape moving in the first place. Tracker software was then used to track each individual position at each frame as shown in this clip. The data was inputted into Excel, and when the X position was graphed versus time, this graph was obtained for the observed position. When creating the computational model, the mass was left unchanged, as it should not have an impact on the tape's velocity, as there is assumed to be zero net force. The tape's initial position vector was set to 0.95200 meters, which was taken from the tracker data. The initial velocity was calculated using the positions at t equals 0 seconds and t equals 0.1 seconds to minimize uncertainty in the calculation. The velocity was then calculated at negative 0.3200 meters per second. The time of simulation was then set to 2.8 seconds, as the tracker clip was also 2.8 seconds. The net force was also left at 0 newtons. The position of the ball was then updated using the position update formula as shown in the last line of the screenshot. This is a plot of the predicted position along with the observed position. The predicted trajectory shows the tape moving at constant velocity towards the origin, but it overestimates the distance that it travels in 2.8 seconds. Both position time graphs show a linear curve for the first second, but as time goes on, the error between the predicted and observed position begins to grow as the tape begins to slow down. The fact that the tape slows down explains why the curve of the observed position versus time was not linear. This indicates by Newton's second law that there must have been a net force acting on the roll of tape, causing it to slow down, which can be attributed to friction and air resistance, which the computational model failed to account for. Possible sources of error include parallax error when filming the tape's movement, which causes some inaccuracy in the measurements of the tape's observed position. There might have also been human error associated with manually tracking the tape frame by frame, which may have caused the tape's recorded exposition to be different from reality. If the axes were flipped and the experiment was repeated, the curves would be flipped and the position time graphs would have a positive gradient. The rest of the physics, however, would stay the same. And in the model, when the net force is set to 0, we can say that there are no forces in the x direction. The tape experiences the downward pull of gravity from Earth in the y direction, which is balanced out by the normal force of the table pushing up on the tape, giving a net force of 0. However, we know that in reality, the net force isn't 0 and that air resistance and friction come into play.